Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to talk about two really important concepts in linear algebra called kernel and range of a transformation. And you're going to see that they're actually very similar to other things that you've heard before, but just kind of a different name. And that happens a lot with this unit because we're sort of just abstracting stuff we've learned, and the term kernel and range are really what in practice people use all the time, not something else that I've already actually told you. So you'll see when I get to that. But to start off, I just want to do another one of these problems where I want to determine whether or not a certain transformation is linear. And so the transformation is defined by taking any square n by n matrix, sending it to the reals by just calculating the rank of the matrix, okay? And when I do problems like this, like whenever I want to show something linear, I do kind of think first a little bit about like, would it make sense that this thing's be linear or not? And my intuition is that it would not. I don't see any reason why that transformation should be linear. So then I kind of start thinking, well, how could I come up maybe with a counterexample to this? You know, there's two properties that you need to like, you could kind of work off of. You could sort of try to contradict the scalars being pulled out part, or you could try to contradict the fact that like t on a sum should equal t on the parts of that sum. And you can do it with the second thing I just said. So you can come up with a contradiction. So one thing to remember, right, is that A is invertible. If A is invertible, I should say, probably just throw an if in here, then the rank of that matrix is n, for like an n by n, right? So maybe I should do n by n here. Basically, you know, that's a property of, you know, we've seen that before way back. I think we saw that maybe even in first semester. But if something is full rank, if something's invertible, then it's full rank. And we also know that like the rank of minus A should just be for the same matrix A. Okay, maybe I'll throw in n by n. It's still n. Doing minus A doesn't really change anything, right? So this is kind of how you could come up with a contradiction. So we know that if t is linear, t of like u plus v should equal t of u plus t of v. But notice if we do this here, so t of, so I'm going to use this rank n matrix A. T of A minus A, okay, would equal T of 0, which equals 0, right? This is like 0 matrix. But T of A plus T of minus A equals the rank of A, which is n, plus the rank of minus A, which is n, which equals 2n. And since clearly 0 doesn't equal 2n, this implies t is not linear. It can be kind of hard to come up with those things sometimes, but that's kind of how I think about them. I think about, well, would it make sense that the transformation be linear? And you got to kind of use that intuition a little bit. But yeah, that would be how you could show that that thing is not linear. All right, so the real plan for today, like I said, is talk about this idea of a kernel and the range of a transformation. So I'm just going to kind of read through the definitions and talk about them a bit first. So if you've got a linear transformation, the kernel of it, which we do denote with this ker of t, is the set of all vectors in V that are mapped by t to 0, to the 0 vector in W. So basically t of V equals 0. This should seem very familiar to you. The range of t, which we denote literally range of t, is the set of all vectors in W, so in the output space, that are images of vectors in V under T. So basically, we get this thing where for some W in W, W equals T of V, where V is in V. And this is kind of the picture you should think of. If the transformation goes V to W, the kernel is like a subset of V, subspace sort of V, and it lives in the domain space. And these are the things that get mapped to the 0 vector over here. And the outputs of all the vectors V live in what we call the range, that shaded area. Now, this region can be larger than the range still. There's all sorts of transformations where you don't hit all the outputs, here. But the range is what is directly transferred from the transformation, okay? So these concepts should seem very familiar. Kernel is really just the abstract vector space name for, of course, the null space. And null space is just what gets mapped to 0 by the matrix. And now we're just talking about abstracting this concept of a matrix to all sorts of different things. And we call it something different. It's called the kernel, but it's a null space. And the kernel is a subspace of the domain, or that space V if we use the symbols. And the range is a subspace of what we call the codomain, or W. And the rank of a transformation is the dimension of the range, and the nullity of a transformation is the dimension of the kernel. Okay? And this is just another picture that's sort of showing you the same thing, just fancy colors, so it's kind of nice. So you got your domain over here, okay? Y is your codomain, and your range is living inside of your codomain, and you just map, into that yellow space, then that yellow space is your range, and whatever vectors over here go to the 0 vector here, those are things in the kernel, okay, which is not really shown here, but that's the idea. So just think null space and just output, input, output, like function kind of idea. All right, so to kind of show this in practice, I just want to compute all these different things for the transformation of the differential operator, which we do call D in linear algebra, and it just sends, order 3 polynomials to order 2. You could do it for higher dimensions, but we're just going to talk about it for this transformation, right? And so we can start really anywhere. Let's just start with the kernel. So for the kernel, we know that the derivative would send any constant to 0, right? So the kernel is really just the set of A such that A is something in R, okay? And that could also just be understood as the P0 polynomial space of order 0, okay? And so from that, you can also get the nullity, right? The nullity then of this transformation D is just going to be, nope, not 0, sorry, 1. This is a one-dimensional vector. That's when we write it in a table with numbers, we would put an A in the first component and then zeros elsewhere. But it's a one-dimensional thing, kind of like an I-hat, sort of. For the range, I kind of think about it is like this. You get quadratics, right, from derivatives on cubics, right? So your output, right, that you're getting, your range, is basically any polynomial of order 2, right? So this thing should have dimension 3, right? And we can check the rank theorem. All that stuff should still work. The rank of a matrix or a transformation plus the nullity of that transformation should equal the dimension of the domain space, basically the idea, right, is just the stuff that gets transferred plus the stuff that goes to 0 should add up to the total stuff that you're sending, right? And so we know that this polynomial space has order 4, right? We know this is 1. We just talked about that up there. And this is 3. And so sure enough, 3 plus 1 equals 4. Mind-blowing math there. And so, yeah, this is kind of how you can like start to break down different transformations in linear algebra. You just kind of go through and, decompose it into like what gets lost and what doesn't get lost. So one cool thing that we can do now actually is there's actually a matrix which represents differentiation. And it is actually true that every linear transformation has a matrix representation. That's something we can talk about later. But D is a linear operator, and so it does kind of make sense that it should have a matrix. There is actually a distinction there, and not all linear operators have matrix representations, but this one does. Okay. So what we're going to basically do is we're going to utilize this fact that we talked about in the last video that said a transformation is basically defined by what it does to basis vectors. One of the first things that we saw way back in this course in some of these beautiful 3 blue 1 brown videos is he was talking about how if you have a matrix like 1 2 3 negative 1 or something, this vector right here represents where I hat lands post transformation, while this one is of course where j hat lands. And so I'm basically just going to utilize that idea, okay? And that's what this statement that I was talking about in the last video really means. It says you can sort of figure out what a matrix will be if you just look at what it does to basis vectors. In terms of the derivative operator, right, it sends nth order polynomials to n minus 1 polynomials, right? So there's actually a notation for this. The constant 1 is mapped to 0, right? And this is actually a formal notation. This means you're taking one specific vector and you're mapping it to one specific vector. And so in kind of our table with numbers representation, right, this means that 1 0 0 is getting mapped to the 0 vector. And then you could talk about how x gets mapped to 1. Otherwise, in table with numbers world, that looks like 0 1 0 gets mapped to 1 0 0, right? And let's just do one more. So x squared gets mapped to x, right? And so in a table with number setup, 0 0 1 gets mapped to 0 2 0, right? And so we can basically now put this together. We can take this, and this, and that is where, I hat lands. This is where j hat lands. This is where k hat lands. So if we were doing a 3 by 3, right, this is what the 3 by 3 derivative matrix should look like. 1 0 0 there, 0 2 0. And the cool thing is you can test it. This is pretty easy to do if you just take an arbitrary polynomial. So this would represent should represent a cubic being sent to still make that mistake. A quadratic going to, it should be a constant, right? So this is a plus bx plus cx squared. And if we just do this thing out, so notice you're going to get, let's see, 0, b, and 0 plus 2c, and then a row of zeros there, so that'll be 0. And so what this is really saying, right, is that a plus bx plus cx squared, the derivative of that thing really is, right, b plus 2cx. And so you can see it, the b plus 2cx is right there, right? And all we did to figure that out is look at where basis vectors sort of go by doing this sort of thing. And this actually extends really, really nicely to higher dimensions. So it's probably not surprising to think that that there should be some sort of pattern to this. And you can already kind of see it. And it's actually is true. If you wanted to do a next order up derivative, you'll have 0, 0, 0 all down there. 1, 0, 0, 0. 0, 2, 0, 0, 0, 0, 3, 0. And that would act as a derivative for, cubics, basically, operating on cubics. And you can just extend that, this diagonal just keeps going. You can also do things where you're doing like second derivative. So that's kind of neat. Like say we wanted to take the second derivative on a quadratic, basically. So you can literally just do 0, 1, 0, 0, 0, 2, 0, 0, 0, and you can square it, right? And then you can just, you can test it. I'm not going to do it out right now, but we know that if we take the second derivative of this, we should just get 2cx. And I promise you, if you do it out, you just get 2c. Sorry, don't know how to take derivatives anymore. You get 2c there, and then you get 0, 0. And if you multiply it out, you'll see it. If you square this, you do one application, it acts as one derivative. Second, acts as second derivative. If you want to take a third derivative, this would be cubed, and what you'll notice is actually if you cube this matrix, it'll go to 0, which is why you're going to get the 0 vector, because we know if you take a third derivative or a fourth or fifth or whatever of x squared type things, it goes to 0. And so this is actually one of those nilpotent matrices where that basically eventually goes to 0 with successive multiplications. And there's also like a integral matrix, if you want to think about that too. I'm not going to get into all of that right now because it's just going to go on forever, but there actually is a n by n minus 1 matrix, which represents the concept of integration. And it's probably not super surprising that it's not square, because we know that if things are square, right, then it's sort of like staying in the same dimension in the transformation. But like a integration, right, goes up in dimension, and so there is going to have to be some weird things where you're jumping up in dimension if you operate on a vector. So yeah, you'll see. I bet you could figure it out if you wanted to play around with it. It should be not horrible to probably figure that out on your own, and maybe we'll talk about it in class sometime. But yeah, I think this is kind of a neat thing to see, how you can start representing transformations with matrices like this. So I just want to talk about one more matrix problem where we're analyzing kernel, range, rank, nullity, all this stuff, but this time do it with an integral. This is probably the most calculus-heavy day of linear algebra we're going to have all year. Been talking about derivatives and integrals the whole class. So to do this, let's just start by taking an integral. So we're going to take an integral. This transformation just sends linear functions to the real numbers, okay, and sends it based on this instruction. So we're really just checking, right, the area above or below the x-axis, between the curve, the linear function, between 0 and 1. And so we are just going to start off and take an integral. One of probably only integrals I take all year. So I'm just going to do an arbitrary like AB linear function. And of course we take the integral. We're going to get ax plus bx squared over 2, evaluated from 0 to 1, which I think I can squeeze this in here. This is just going to be a plus b over 2, right? And so if we're talking about the kernel, right, then we need a plus b over 2 to equal 0, or just a to equal minus b over 2. So the set where you get linear functions of minus b over 2 plus bx, such that b is some like real number, is the kernel. And this thing has dimension 1, right? And one of the neat things here, you can kind of see this. If you take, like, say, let b equal 1, right, you're going to get x minus a half, right? And so between, let's see, 1, we're going to say is there, we're going to say that's a half. So that's about -1, that's 1. So this should be in the kernel, right? That kind of linear function. And if we plot it, right, we're going to get this point, and then if you plug in 1, you're going to get a half. It's up here, and it would just be like that. And, you know, certainly the amount of area that's here is equal to the amount of area that's here. And so those would zero out, right, and it would give you 0 in the interval from 0 to 1. And you can do a few more just to kind of see what's going on. Like if, I don't know, let's let b be 2, right? Then you're going to get 2x minus 1, right? So you get minus 1 there. If you plug in 1, 2 minus 1 is 1. And so you're going to get, oh, I missed it. You're going to get that, okay? And now this area, right, and this area are equal. And this could just keep happening. You could do other ones, but you're always going to get this symmetry going on. And so anything that sort of is in the span of that line, that's a one-dimensional thing, that would be in the kernel, okay? So to get the rank of the transformation, the range and all that, I mean, you could use the rank theorem, honestly, if you wanted to now, just kind of do it a different way than we did it before. We know that the dimension of P1, which is equal to 2, needs to equal the dimension of the rank of T, or here it's S, sorry, plus the dimension of the nullity. I don't have room. We're going to go just down here. Dimension of the, well, called the kernel of S. And so we know 2 equals something, plus we just talked about how that needs to be 1, so this needs to be 1. And so that's your rank of the transformation. That's your nullity of the transformation. They are the same. To describe the range, right, you would just want, let's do this color. The range is just basically a plus b over 2. That doesn't equal 0, right? Anything in that set. So you could say like just the set a plus b over 2 such that a does not equal minus b over 2, right? And I guess a and b are all real numbers. Anything in there, right, where you're not going to get this symmetry, and so you're not going to be able to zero it out like that. So that's just another kind of neat example to analyze all these different properties of a transformation.